Greetings once again. My name is John Gabriel and this is a new calculus channel. So in the previous video I talked about the abstract unit in algebra and where does it come from. And I gave you a lot of information, which of course is in chapter 3 of my book, but of course the formation of number is shown in chapter 2 where the foundations are laid. Chapter 3 describes more of the arithmetic, and chapter 4 the basic operations. But now what I want to continue talking about is the differences between geometric measure and algebraic measure. So in geometry we have exact measure and we can perform all the 4 basic operations of arithmetic using ratios of magnitudes. Okay, so we can, for example, multiply. Geometrically we can do this. We can multiply square root 2 by pi and get an exact line segment. Okay, and you'll see a demonstration of that in that video which I gave a link to in the previous section called Symmetry of the Circle. Okay, so, and of course you can do anything else. You could say square root 2 divided by pi, or pi divided by square root 2, or anything else you like. In geometry the result is always 100% precise. Okay, so algebra sacrifices precision for generality. In other words, what we do in algebra is we want to, for example, if we have, again, let's take this square root 2 symptom. So we want to, in algebra, we want to get away from having to write this line segment down like that as a ratio and the side. Okay, so we want to get away from that, right? Well, naturally we can say that this side measures up to there. And measure, by the way, measuring a line segment like that is like division because you're subtracting the side from it, right? And then of course you want to know how much of this side to subtract this tiny portion here. That's not a problem. You could just put a divider on there and pull it off here and you've got the answer. So your answer will be that the side measures the diagonal with one of these and that much of the side, that much of the side, okay? Or this one, because we're looking at the same length. So in geometry the result is precise. Now we could also in geometry say, if we wanted to, is divide using a geometric technique into any number of equal parts, the sides, okay? Meaning that we can refine this measure here. And this is what happens in algebra, okay? So in algebra, that's exactly what we do. We divide the side, or the consequent, we take the consequent and we find an equal number of consequents that will measure at least once and then tell us how many of these are in this section here. So typically if we take divide each side by 10, we're going to get 1.4, right? If we divide both sides by 100, we're going to get 1.41, and by 1,000, 1.414. Okay, and so this is the constant that is realized as square root 2 in algebra. Okay, so square root 2 is not equal to this. It's never equal to any of these approximations, but in an actual calculation in algebra you have no choice but to use rational number approximation. And of course rational is redundant because number implies rationality and rationality implies number. So that's what we do in algebra. We take the measure of the ratio, okay? In other words, you take the measure of the diagonal, this part here, the whole part, to the side. And we say it's approximately 1.4 or 1.414. And we call that constant root 2. All right? So that's all you can do in algebra. Algebra is never precise. And you can, and when you use this in an equation or whatever you use it for in an expression, it acts exactly like a variable x would act. Okay, in other words, it's assumed to be a number. So in any calculation, you're not really dealing with something that is a number. You're dealing with only a special part of it that is a number, okay? Because you can't really find the value of square root 2 or pi or many other numbers such as e, etc. So just to summarize, let's reset the canvas. So in essence, if we look at all these things, by the way, are in this great book that I've written, the Ultimate Book of Numbers. Everything is in here. So if you really want to understand number, this is the best book ever written on number and number theory. Nothing beats this, by the way. There is nothing that has been written that even comes close to this book that I'm giving to you for free. Okay, so basically number, we begin by saying that 1 over 1 is the measure of a certain magnitude. If we're talking about day, we're talking about a period. Okay, if we're talking about length, then we have 2 line segments. So this gives you many examples and also some exercises which you should do because those lead to understanding. And of course in chapter 2 we look at the foundations which are laid. Okay, so in chapter 2, I give you a complete summary of how we get number. And by the way, natural numbers did not come first, contrary to what your moronic professors and teachers tell you. In fact, natural numbers come only after rational numbers have been established. Okay, so, and in actual fact, we don't even need to have rational numbers to go to a fraction because we use the natural numbers as a name to decide how many parts are in the consequent and in the antecedent. So, of course, we say, okay, let's call that 1 over 1, let's just call it 1. And 2 over 1, let's call it 2. And then we say, okay, we can form any fraction by simply counting up the number of parts so if we've got a ratio of natural numbers, like let's say 2/3, then we say, okay, the measure is equal to 2/3, okay? So 2/3 is a number. 2/3 is a number or a name that we give to the measure of a ratio of magnitudes. Well, in this case, because we're talking about a fraction, it's a ratio of numbers, right? Otherwise, it's a ratio of magnitudes. And if it can't be measured, then it means that you have what is commonly and incorrectly known in the mainstream as an irrational number. It's not a number at all, because if it were a number, then this measure would be possible. Okay, so that's the entire theory behind numbers. And of course, I give you a lot of information in this booklet, and I explain to you how ancient Greek construction workers were actually able to do all the 4 different operations of arithmetic with 100% accuracy without even knowing a thing about number. So all they knew how to do was to use a compass, right, and a straight edge. That's all they knew how to use. They knew nothing about numbers, nothing about arithmetic operations, and they were able to do all these calculations which even the most advanced computer today can't do using algebra. Okay, but geometry is 100% precise. So I intended this as a follow-up, which I'll call part 2 to the previous series. So once again, if you're not a subscriber, become a subscriber. Go to my academia profile, okay, and become a follower. Become a follower. So go to my profile here at this link, John Gabriel 30, and follow me, and you'll always be notified anytime I upload a new book or a new article, and also become a subscriber on my YouTube channel. That's pretty much it. I'm John Gabriel. This is a new calculus channel. Goodbye.